You bent it?
But it doesn't matter, right, for Lewis structures, the angle? No.
The angle doesn't matter for Lewis structures, but sometimes I ask you for a 3D drawing, and then it matters. For example, like carbonate. Let me just draw this one more time. Carbonate is, what's the geometry of carbonate? Trigonal planar. When we look at this, what are the bond angles in trigonal planar? 120. And so in this sense, it's trigonal planar, 120 bond angles, and it's going to have a shape like this. But what else would we want to know? We'd want to know its polarity. We'd say that this is a monopole. But sometimes we want to dig even deeper. You know, if we dig deeper into this, then we'll see. Is it a monopole? If it's a monopole, is it like, is the charge, the -2 charge, evenly distributed in the ion? What would you say? In other words, this whole thing carries a -2 charge. And so this is shaped like a triangle. And so when I look at the triangle, is the -2 charge distributed evenly over the structure, spread out evenly? We say, no, it isn't. And so in a sense, well, polarity we usually use in terms of solubility, right? And so in terms of solubility, fine, monopole's fine, because it's going to be polar and it'll dissolve in polar liquids, right? But in terms of chemical reactivity, then we don't want to just treat this object as being, you know, a -2 object that with a charge that's evenly distributed over the entire structure, because all chemical reactions are electrical in nature, and therefore we need to look at how the charge is kind of distributed. And so when you look at the charge, what is the charge distribution like? Well, the charge distribution is like, this is -2/3 right here, -2/3 here, -2/3. In terms of formal charge, what's the formal charge on carbon? 0. And so we see that the oxygens carry the negative charge density, correct? And the carbon is kind of break even as far as charge density goes. But we could dig into this even deeper. And so we got a ring of negative charge around here, correct? Ring of negative charge. Now, when we look at it, when we do this, do you think these bonds are 100% covalent? No. So what we're going to do is we're going to look at the two extremes. One extreme is assuming they're 100% covalent. The other extreme is assuming they're 100% ionic. When we do 100% ionic, what number do we generate? We generate the oxidation state. The oxidation state of oxygen is going to be -2, -2, -2, and the oxidation state on carbon is, oh, actually, did I get this right? +4. And so take a look. When you sum up the oxidation states, we get the net charge. When we sum up the formal charges, we get the net charge. And so the net charge is either the sum of the oxidation states or the sum of the formal charges. Do you want to compare? Do we compare the red numbers with the green numbers? Never. Never. We can compare red numbers with red numbers, and then we're a bit more specific here. And so what this says is this. You know, this bond is polar covalent, correct? Polar covalent means it's between the extremes of ionic and covalent. And so, you know, the true picture is the charge on carbon is not really 0, nor is it +4. The charge is somewhere between 0 and +4. The charge on oxygen is not -2/3 and it's not -2, but it's somewhere between -2/3 and -2. And yes, what could we do? We could do quantum mechanical calculations to determine or pinpoint that charge, right? But that means doing a calculation. This we can do by hand. And we know, what the range is in the charge. So this is why this is very powerful, because we see that the oxygens are going to carry all the negative charge density, and the carbon is going to have positive charge density. And so if something were to attack this, then we'd see that, We'd see that oxidizers probably want to attack the oxygens, and reducers will be attracted to the carbon. Oxygens are perfectly happy at -2 though, right? And so probably carbonate will be a oxidizer. Do you think carbonate is a very good oxidizer? Why? Huh? Do you think carbon will be a very good oxidizer? Yes or no? Why not? Carbon has a +4. Shouldn't that be a good oxidizer? +4?
It's surrounded by the
No. Okay. This is remember our science is a two-pronged approach, meaning that it's a mix of theory and experimental observation. So the theory, yes, it's +4 oxidation state, which means, yeah, it should be a good oxidizer, but we know, +4 is electron poor or electron rich? Electron poor. +4, that's a lot of electrons to lose. What is I4? I1, I2, I3, I4. By the time you hit I4, how big is that? It's big. To ionize that last valence electron on carbon is going to cost you dearly, right? And so carbon at +4 you'd think would want electrons badly, but we know based on experiment that, is it a powerful oxidizer? No. We know that because of our knowledge of the redox chart. If it were a good oxidizer, then we'd probably have seen it, because carbonate is a very common ion, right? And so this is a mix. Whereas, hey, what about nitrate? Nitrate's similar. Actually, maybe we should do nitrate. Nitrate's very similar. Trigonal planar. 3 resonance forms. Hybrid that looks similar. Formal charges are different. -1. Nitrate. Is it a powerful oxidizer? Well, what is it? Nitrate has a +5. And so if we were going, this is +4, this is +5. We'd say, well, if carbonate is not a very powerful one, then nitrate's probably not very powerful either, right? Is that right? No, that's not right, because from factual knowledge that, yeah. So do you see? They're different. Yeah, they're different attitudes towards this. One attitude is, why do I have to memorize all this stuff? Why can't I just have a simple rule or a simple law? Tell me the rule. Give me a simple rule to do that. There's no simple rule to do this, right? It's got a lot of memorization. This is why I put on the first test, memorization, because a lot of people hate memorization. They say, just give me the number. It's a +5, though, that's a powerful oxidizer. +4, that must be still a powerful oxidizer, right?
Wait, so would that mean that our understanding of that is failing us, or it's just the nature of that?
No, nothing's failing you. We're just doing this on pencil and paper.
Disagree. If we, for some.
There's no disagreement. There's no disagreement because it's a different element. This is carbon, this is nitrogen. You can't treat the two the same. Also, Yeah, so the point is that what was what were we looking at before that had something similar? Well, you know, anybody can calculate the number, right? There's a very famous quote. A very famous quote by one of the physicists. He said, you know, to boil it down, this is my interpretation of his quote. His quote is that anybody can calculate this number, right? It's so easy. But that's not science. You know, science is not calculating numbers. Science, because a computer can do that or whatever. Science is interpreting the numbers. You know, you have your computer spit out a number, but how do you interpret that? Well, I guess you can come up with a computer program to do that, but that would be a very complicated program, wouldn't it? Because it has to take into account very many factors. So it's not anybody can calculate these numbers, right? That's not a big deal. If I test you on that, so you can calculate the number, you can figure out the oxidation state, but do you know what it means? That's a much more bigger deal. And so if there's going back,
I was just wondering, how'd you, going way back, how'd you calculate the terminal charge for carbonate if it was 2/3?
the negative 2/3?
Yeah.
I didn't calculate this. This number came from the resonance forms, averaging the charge, the -2 charge over 3 oxygens from the resonance forms. Calculating this is a bit more of a pain. I mean, we could calculate it, you know, because this would be 2 floating lone pairs, so there'd be 2/3 of a lone pair here, and then 1/3 here, so it'd be 1/6 of an electron plus. You could calculate it, but it's just not worth it. It's much easier doing it off the resonance forms.
Does every polyatomic ion have like resonance state, or is
No.
some of them?
Some of them.
So how do you know which one has like the resonance?
Because when you're given a choice where to make the double bond, that's when you know you're going to have a
So
resonance.
do you assume that whenever you have a double or a triple bond, then you assume that?
No, it's when you have a choice. If there's no choice, for example, here, there's no choice. Is there a choice? Could I put the double bond here?
No.
Could I put it here? No choice. This is only one structure. There's no resonance forms. Here, there's a choice. Could I put the double bond here? Yes.
Yeah.
Could I put it here? Yes. Could I put it here? Yes. Here's a choice. Therefore, there's.
There'll be 3.
So you think every probability,
Huh?
you think every choice that you can make?
Yeah, right. You do every choice that you can make within a certain. I mean, these are all the resonance forms we've been doing so far. What we call energetically degenerate. I mean, they have the same energy, right? And so that's why I picked nitrous oxide. Nitrous oxide is a challenging problem. What was the skeleton you guys generated for this?
Oxygen in this and
Oxygen is in the middle? All right.
that's what I thought.
Oxygen in the middle and then the 2 nitrogens?
That violates
Oxygen, that doesn't violate anything because I just said this is a general rule. A general rule of thumb is that the least electronegative element goes in the center, but oxygen often goes in the center, like for example, water. It's in the center of water. Oxygen is also in the center of things called ethers, like this, CH3O, CH3. This is called dimethyl ether. So we can have oxygen in the middle. It's a bridging atom. There's no problem with that. Okay. But in general, we like to put the least electronegative. And so why did you put oxygen in the middle and not the least electronegative?
Well, it makes better. To me,
It's more symmetric, yeah.
Makes sense.
It looks better, okay.
but it's not right.
All right, now let's finish this. That takes care of 2, 4, and then what did you do? You complete the octets to the outer?
Yes.
Good.
And then you make double bond.
And then we'll make a double bond. Which one do you want to pick? Now, do you see there's going to be resonance? There's got to be resonance because we can pick the left nitrogen or the right nitrogen. Which one do you want? It doesn't matter. So just pick one, right?
Yeah.
But we're still short, and so now, what should we do? Should we make a triple bond?
No.
No, it doesn't make sense. We'd make a double bond here, right?
Yeah.
Then we're good.
But
And so everything has an octet, we're good, right?
No.
What's wrong with this structure, if anything?
Just wrong.
The formal charge, right? What are the formal charges?
We go plus nitrogen
Minus 1 plus 2. Minus 1 minus 1 plus 2.
Okay, -1 plus 2. Yeah, chemically, does this make much sense? That the nitrogen's ganged up on an oxygen and stripped 2 electrons from it. Okay, one reason it doesn't make sense is I1 is okay, I2 is pretty big, a lot bigger, right? To strip the second electron off oxygen is going to require a lot more work than the first electron off oxygen. Okay. Number 2, who's stronger, nitrogen or oxygen? Oxygen. So, well, I guess if you have 2 nitrogens, maybe 2 nitrogens beat an oxygen? No, but you don't think in terms of that. You just think in terms of one bond here. You look at this bond, who won? Nitrogen. But the thing is, when oxygen loses 1 electron, do you think it's going to put up a more vigorous fight for losing the second electron? Yeah. Because it's the effective. And so here, there's big problems with this because the formal charges don't make sense, do they? Chemically, they don't make sense. So maybe it has. So maybe we leave it like this, or maybe we look for a different structure that might be.
Place N in the middle.
Place N in the middle. Okay.
Let's try that.
We'll try N in the middle, and then see what we got here. If we put N in the middle here, then we'll put like NNO.
Can't you not change N? Yeah, 'cause isn't carbon like the only thing you could chain together? Like that?
No, you can chain N
Okay. Which ones can you chain together like that?
a lot.
Oh, I didn't know.
The only ones you can't are hydrogen and fluorine.
Oh.
Hydrogen and fluorine do not.
Weird.
Let me well, I'll talk about it. All right, now we got 16 electrons, so let's complete this, and then okay. Well, who's going to sacrifice their electrons first for nitrogen, the middle nitrogen? The other nitrogen, don't you think? It's weaker, so we'll sacrifice it first. Okay, now nitrogen sacrificed some of its electrons. Who's going to sacrifice next? Because we still don't have an octet. Nitrogen again?
Yes.
Nitrogen again.
It'll be 10.
It doesn't look right. Okay, let's well, this now we're stuck with this structure. What would you say? What would you say this? Maybe we have the oxygen sacrifice a pair of electrons like this. Still doesn't look right. So what else can we do?
Oxygen in the middle.
Well, we did oxygen in the middle here. Huh? All right, let's look at the formal charges here. Okay, here this is 0.
Plus 1.
plus 1 and
Minus 1.
minus 1. Okay, this is 0, plus 1, and minus 1. Okay, over here, what do we have?
Minus one on and
Minus 1,
Plus 1.
plus,
zero.
and 0.
Oh, they could do residence.
Right.
Most of them right?
Yeah.
That's a different-
Do you see, these are what we call inequivalent resonance forms because they have different energies. But the thing is, this is a tug of war between oxygen and nitrogen. Who should win? Oxygen. But is nitrogen going to be a complete loser, you think?
No.
No. If you had a tug of war between oxygen and nitrogen, oxygen's not going to win 100%. Right? And so here we have oxygen winning 100%. Here we have nitrogen winning 100%. Right? But we know oxygen's stronger than nitrogen, but they're right next to each other. They're both strong. And so what would you say? Well, we just take a guesstimate. Let's say maybe it's 80% this and 20% this as a guesstimate, you know? Because it's like we're going from a 3.5 to a 3, say, in terms of the opponents. Or something like that, you know? Do you see what I'm saying here? And so what we have is we have inequivalent resonance forms. So the hybrid is going to be a mix of it, but it's going to be a bias mix towards this structure than this. Does that make sense? And so what this means is we're going to see a hybrid that's going to look something like this because these are inequivalent resonance forms. We know that the oxygen should be more stable, a little bit more stable than having the charge of nitrogen. And so what do we have fixed? We have fixed a lone pair of nitrogen and a double bond here, and a single bond we have fixed here. Okay, on oxygen we have 2 lone pairs fixed. Okay, now we're going to have 1 lone pair that's going to be split between the 2, but the lone pair is going to spend more time around oxygen than around nitrogen. And so maybe we end up with something like this. Maybe we end up with a minus 0.8 charge on oxygen and maybe a minus 0.2 charge on nitrogen because it's an uneven tug of war. You know, this is just guess. The guesses. Guesstimate. Okay, so what that is going to mean is this. That the double bonding electrons spend more time in the nitrogen-oxygen bond than in the the double bonding electrons spend more time, not double bonding. This extra bonding pair spends more time in the nitrogen-nitrogen bond than in the nitrogen-oxygen bond. And so this bond would be something like a 2 and, let's say, a 2.8. And this would be like a 1.2 bond. In other words, all we're doing is we're trying to delocalize or spread out the electron density, but the electron density is going to, oops, sorry. The electron density is going to spend most of its time, the bonding electron density is going to spend most of its time in the nitrogen-nitrogen bond, right? And the lone pair is going to spend most of its time on the oxygen. And so it just spreads out uneven. So what this is like an uneven tug. You know, over here we have a deeper tub. Over here we have a shallower tub. And we think of the electron density as the water. So the water is going to sink down here. Before we had even tubs because both bonds and both resonance forms were the same, right? In the hybrid, actually, this is the hybrid over here. The hybrid. This is for the bond.
Professor, can you explain about the delocalized being on the time? What do you mean by delocalized?
What do I mean by delocalized? What I mean by delocalized is this. Let's say you have a tub like this, bathtub. Over here we have the left bond, this triple bond. Over here we have the right bond, right? Over here we have 3 times as much electron cloud. For analogy, we're going to call it 3 feet, right? Over here we have 1 foot. The problem is there a wall between these? There's no wall between these because we just take these, pop these out, and we get that form there. In other words, electron density can redistribute in the molecule. Over here, what do we have? Over here we have 2 feet and 2 feet. So it looks good, right? But it turns out that this side is actually more stable, which means what?
Quiet.
Yeah, and so the tubs aren't even depth like that. It turns out that this tub is a little deeper than this one. And so more of the water accumulates here, 2.8 feet, and we only have 1.2 feet here because it's uneven now. These aren't equivalent resonance forms. Does that make sense?
Figure out the things in the lab is more common.
How did I figure out that this is more common?
Yeah.
Because what? This is a tug of war between oxygen and nitrogen. Who should win, oxygen or nitrogen? Oxygen. And therefore, that one's more stable. But is it a, do you think it's a winner-take-all situation? No, because nitrogen is going to put up a fight. Is it going to put up a strong fight? Yes, because nitrogen and oxygen are almost even in strength. The 3 most electronegative elements are fluorine, oxygen, and nitrogen. You have 2 powerful opponents facing each other. It's not going to be a one-way dominant victory for oxygen. It's going to have to fight. The oxygen's a little bit stronger, right? And therefore it's going to pull that electron density for the lone pair. This. And so normally, you know, if it were an even fight, we'd split it down the middle. Oxygen takes 1/2 of this and nitrogen takes 1/2, right? That's what we did for the other one. And so it'd be an even fight, 1/2 and 1/2. We share evenly. But here, oxygen is stronger. And so it's not 0.5 and 0.5. This is just a guesstimate. Oxygen is going to be more dominant, therefore it's going to get something like 0.8. Whereas nitrogen is not going to be a total loser, it's going to keep some, 0.2.
So like if you run on Sparta, would it show both of them?
I'm sorry, if you...
On Sparta?
No, if you run it on Spartan, you just see this.
Oh, okay.
You see this. If you run this on Spartan, this is what Spartan's going to show you. Spartan's going to show you it's not 0 and -1. It's not -1 and 0. It's somewhere in between. Is it halfway between? It would be halfway between if these were equal. And so what Spartan's going to show you is you click on this atom and you'll see, oh, it's, where did I get 0.8? It's about 0.8 on Spartan. And so this tells you that oxygen pulls more electron density. And so this is some information we can get from Spartan. Yeah. But the thing is, do you have, $2,500 you want to spend on Spartan? I got a calculator. Why do I need to memorize multiplication tables? That's what I heard. I heard that in elementary they don't make kids memorize multiplication tables because, well, I don't know if it's true. But I just heard they don't make kids memorize multiplication tables because there's a calculator. Well, I just read that, yeah. I don't think it's true. But, why do I need to do this? Because there's Spartan, right? But not everybody's going to have Spartan. You're not going to carry Spartan on your phone. So and also it's expensive. Nobody wants to buy Spartan, And so this is what we could do on paper, right? And get something that's close to Spartan so far.
What if your guesstimated number is right?
What?
How are you getting to, I'm still unclear where the 2.8 and 1.2 are going to be.
I don't, okay. I'm just guessing. If this were an even match, then it'd be 0.5 and 0.5, a tie, right? That's a tie. So we take one electron and split it, the density, the cloud. And so it's a tie now. But it isn't an even match. And so what? Oxygen's stronger. So yeah, so I could have guessed, well, oxygen's stronger. So this is 0.4, this is 0.6, right? If oxygen is just a hair stronger, but oxygen is more than a hair stronger because oxygen is a 3.5 on electronegativity and nitrogen is a 3.0. And so it's a bit stronger, 0.5 out of 3 is what? 5 out of 6, about 20% stronger, right? That's how I got it.
The charge, wasn't the charge that was asking the bond lengths, the 2.8 and 1.2?
Oh, the 2.8 and 1.2 it's got to be the opposite. Here we're going to split these as 0.8 and 0.2, right? If these electrons spent all their time here, then it's a 3, right? If these electrons spent all their time here, then it's a 2. And so which one is it? Well, I'm already saying it's 0.8 of this structure. So if it's 0.8 of this structure, then that means these electrons must spend 0.8 of their time here and 0.2 of their time here. 80% of the time here, 20% of the time here. 80% of the time on this oxygen, 20% on this nitrogen. And so this is where I got that, the 2.8, because I'm saying this is about 0.2 and this is about 0.8. Does that sound reasonable though? Yeah. And so that's how I got these. The number for the bond, that's called bond order. Bond order. And we do the bond order because what the bond order tells us is this is stronger than the double bond, but weaker than a triple bond. This is going to be shorter than a double bond, but longer than a triple bond. And so it gives us some kind of idea about the bond length and the bond strength. This is why we want to come up with these numbers like this. Then we use a little bit of experimental data. We know how long a double bond is. We know how long a triple bond is. And so we can come up with some kind of estimate how long a 2.8 bond is going to be. Okay? And then so nitrous oxide is difficult because we have inequivalent resonance forms. But carbonate's a lot more straightforward because all 3 resonance forms are equivalent. And so you just take the straight average. This is called a weighted average. We take more of the left structure and less of the right structure. A weighted average. We can't always form double bonds. Oh, that structure was what? Linear? Nitrous oxide, linear?
Yeah.
Yeah. Polar or non-polar?
Polar.
Polar. You know, asymmetric. It can be polar. We can't always form double bonds. So let's look at a scenario where this happens. BF3. Fluorine never forms more than one bond. Chlorine can, but fluorine can't. Chlorine, bromine, iodine, all those can form more than one bond.
What about hydrogen?
Hydrogen can. Well, I take that back. But in our class, hydrogen cannot. In some, some other species, hydrogen has what they call a 3-center bond that could happen.
You said fluorine, bromine, and iodine cannot form double bond?
No.
Only chlorine can?
Fluorine cannot. Everything else can,
Oh, okay.
except for hydrogen.
So it's a boron, fluorine, and hydrogen.
Yeah, hydrogen and fluorine. Hydrogen and fluorine never form more than one bond. And so let's take a look at this. What happens, because boron has less than an octet, right? And so what happens if I form a double bond? Like that. That means fluorine is giving up some electron density. And so what's the original formal charge on fluorine? 0. When I form a double bond, what happens to the formal charge? It goes to plus. And boron, what's the formal charge on boron? Minus. And so if there's a tug of war between boron and fluorine, who wins? Fluorine. But is this structure showing that? No, this structure is showing boron wins. Is that going to happen? No. Therefore, anytime fluorine forms more than one bond, it has to lose electron density. And fluorine being the most powerful oxidizer and the highest electronegativity species on the periodic table, then it's not going to happen. Okay? Just won't happen. So we're stuck here with this structure. This structure is what shape? Trigonal planar. And so we have to look at the shapes. Do you know all the shapes that we're going to encounter for molecules and ions? Let's review the shapes and then add some shapes to it. These are called molecular geometries. The molecular geometries are based on the electron geometries. We only have a limited number of electron geometries. And so the first electron geometry we'll look at is linear electron geometry. And so in a linear one, we'll have some atom, which we'll call A in the center. We could have 2 single bonds like this. Or we could have 2 double bonds, or a single and a double, or a triple and a single. And so we'll get, when we look at the molecular geometry, molecular geometries of the geometry of bonded atoms. And so here, B, CO2. We also want the bond angle. Yeah, 180. And so the bond angles are defined by 3 atoms. The carbon, well, I shouldn't say. The oxygen, carbon, oxygen angle is 180 degrees. All diatomics are linear.
Generally, all CO or CC.
OCO. OCO bonding. Okay, the next electron geometry, which is called B, is trigonal planar electron geometry. And so we have an atom here in the center. We could have 3 single bonds in this triangular arrangement, or we could have a double and 2 singles, or we could have a lone pair and 2 singles, etc. The double bond is considered one group, and the lone pair is considered one group. We adopt this geometry because we want to minimize repulsions. And so if we think about it, for example here, it's going to be negative charge density, negative charge density, negative charge density. To spread out the negative charge density as far apart as possible, it's going to adopt an angle of 120, 120 degree angle all around. However, sometimes these groups are not equivalent. Well, let's talk about 2 things. One, does it matter the atom? Yes, a little bit. For example, hydrogen versus a chlorine. Chlorine's a lot bigger, isn't it? It's a lot bigger. And so, does it take up a lot more space? Well, we're going to ignore that. When we look at this, all we see are 3 single bonds here in our analysis. And the 3 single bonds means that angle should be 120.
Is it possible to have, doesn't it need 8 electrons around it?
Yeah, it does. This is not stable species. This is just a hypothetical example. It should have 8, but we'll throw a boron in the middle. And then we got to compromise. Will chlorine lose an electron to boron? Make a double bond? Maybe, maybe not. Iodine? Perhaps. Okay, going to this, if we did form a double bond has a lot more electron density, right? And so it's going to require more space than single bonds. If it requires more space, then it's going to distort the angle a little bit. The ideal angle should be 120. And the distorted angle is going to be, well, we got to look. We look here to here. This angle should be a little more than 120, just a little more. So we'll just say greater than 120. This angle here should be greater than 120. And this one here should be less than 120. Now, in this third scenario here, we have a lone pair. Now, the difference between a lone pair and a bonding pair is this. A bonding pair is being pulled like a tug-of-war between 2 atoms, right? Let's say a carbon and an oxygen. So the carbon and oxygen are fighting for that bonding pair here. And so the bonding pair gets spread out between the 2 atoms in the bond, right? But the lone pair, is there anybody else pulling on that lone pair? Nobody. And so what happens is the lone pair generates big repulsions with the other electrons because the lone pair is concentrated on just atom A, whereas the bonding pair is being pulled between atom A and atom B. And so what this does is it creates repulsions, bigger repulsions between these two groups, meaning that the angle is going to be about, well, this angle here is going to be less than 120. Now, you guys recall the Heisenberg uncertainty principle, right? What did the Heisenberg uncertainty principle say? Yeah, are we going to pinpoint the exact position? No. And so what we do is we don't usually write the angle between a lone pair and an atom. You know, and so this is usually never stated. This angle should be greater than 120. But we don't usually include that because the lone pair is, I mean, if we pick this, the middle part of this cloud, then fine, right? But since the lone pairs are somewhere in that cloud, then. But whereas bonds, you know, the nucleus of the atoms suffer from the Heisenberg uncertainty principle? No. So we can pinpoint the positions of these atoms, therefore we can pinpoint the angle. No problem. So that's what we have here.
But also angle between the lone pair to the
Hmm?
single bond.
What is the angle between the lone pair and the single bond?
Yeah.
Greater than 120.
The same thing as that.
Yeah. Okay, it's about 122, 122, 116. This is about 122, 122, 116. So close to 120. Okay. When I say greater than 120, it can't be like 130, you know. It's going to be close to 120. 121, 122, something like that.
So the same thing happens for the double bond, that the Persian is greater, get greater, the more electrons.
Yeah. More electron density. Okay, the next thing is, let's take a look at a couple of example structures of this. Formaldehyde. Formaldehyde, what is the shape of this? Well, this is molecular geometry. The molecular geometry of this is going to be trigonal planar, just like the electron geometry. In the angles here, we have the OCH angle. The OCH angle is going to be what? Greater than 120. And then we have the HCH angle, which should be less than 120. Let's look at another one. We're going to look at this one here. No, this is not it. Sorry. That's not what I want. What do I want?
Jim.
Yeah, this one is going to be bent. Bent. The angle, the FBF angle is going to be what? It should be less than 120.
So that's bent.
It's bent or angular.
How do we?
How do you know it's bent? Because you look at just the bonded atoms. When we look at the bonded atoms are.
Didn't you just call it trigonal planar?
Yeah.
Oh, that's what the third.
There's a
Yeah, it's trigonal planar with the electrons. if you look at the electron, we got a lone pair and two single bonds. It's trigonal planar. But we can't pinpoint the electrons. You don't see those pinpointed. What we see are the atoms. If you were to shine X-rays at this, we're going to pinpoint the atoms here, and the atoms are going to show a trigonal planar or bent geometry. A bent geometry.
So one is trigonal planar and one is bent.
Yeah. The electron geometry is trigonal planar, but the molecular geometry is bent. Basically, we don't care about the electron geometry. We care about the molecular geometry. But the electron geometry dictates the angle, right? And so that's why we need to know the electron geometry. We need to know the angle. Is it linear or is it bent? It's bent. Let's do some more examples here. The next electron geometry is tetrahedral. The tetrahedral electron geometry is like this. You know the angles in a tetrahedron? All the angles are the same at 109.5 degrees. This is what we call spherically symmetric. You know, if you were inside a ball and you wanted to become as spherically symmetric as possible, then you'd adopt the tetrahedral configuration, you know. You'd put maybe your legs out like this and your arms up like this. And that way you could be stable inside a sphere. Okay? And so this is called spherical symmetry. Here, tetrahedral. All the angles are the same, 109.5. Spherical symmetry. And so what I'm trying to show here is this. Two of these are in the plane. This red one sticks out, and this one sticks in. And this is how we typically draw on paper to show the geometry. You know, but what we could have is this. It doesn't have to be bonds like this. We could have a lone pair like this, and then three bonds. Like this. You know, if we have this, then we get the molecular geometry. Is tetrahedral. But if we have a scenario like this, do we count the lone pairs? No, we don't see. They're there, and so we have to factor that in for the angle. But the molecular geometry is going to be called trigonal. Yeah. Trigonal pyramidal. Trigonal pyramidal. And we look at the repulsions here. The lone pair, remember the lone pair is concentrated on A. And so what's that going to do to these angles here? It's going to compress them down. And so the angles that end up here are going to be less than 109.5. And the actual angles are about 107. So 109.5. Three of them. Sometimes we have two lone pairs. When we have two lone pairs, this is the way we draw. One lone pair goes in here. The other lone pair comes out, the wedge here. And that leaves these two bonds here. In other words, when we look at, this is kind of the wedge part of it. This is the dashed part of it. And so this lone pair is coming out with this wedge. This lone pair is going in with the dash.
What did you draw again?
Okay, all I did was, okay, I have my tetrahedral arrangement like this. Like this. And all I did was here's the lone pair sticking out. Here's the lone pair sticking in. And so we got the lone pairs here and the bonds are here. And so the angle here is going to be less than 109.5 degrees. And so it's about 105 degrees. This is about 107 degrees. This is about 105 degrees in terms of the angle.
What is the difference between these two?
One lone pair versus two lone pairs. The geometry, when we have two lone pairs, the geometry comes out bent. You know, just here. Lone pairs we don't. So let's do 3 quick examples of these. The first example, A, is let's go with CF4, carbon tetrafluoride. This carbon tetrafluoride. What's the geometry? What's the angle? 109.5. The next example is ammonia. What is the trigonal, pyramidal, and angle? The H and H angle? About 107. So less than 109, about 107. Okay, the next example is water. But I'm going to draw water like this. One bond coming up, one bond going out, and then one lone pair coming out like this, and one lone pair going in to the board. This is bent, and the angle less than 109.5, which is about, that's about 105 degrees. And the angle is the HOH angle. And you can see the geometry. The geometry is bent like this. All right, so tomorrow we're going to continue this. This is continuing with experiment 8 and 9.